man. I'm super nervous, you guys. Thank you so much for being here and giving me the time to talk to you about my experience. So I'll get started. So before I begin, I want to thank Dr. Kosmatka, Tassine, and Becky in the California Space Grant Consortium for giving me the opportunity to actually be here and speak with you. Because without them, this whole thing would not be possible for me. And I also like to thank these three professors whose mentoring have shaped the ideas presented in this seminar. And it takes a village to help me. And these three people who have definitely been the pivotal point in my journey here at UCSD, because without them, I wouldn't know how it would turn out. And so keep these three people in mind: Carter Morris, Malika Malis-Moran, and Tim Wheeler. So, origins. So I'm going to talk a little bit about myself. I'm a first-generation college student, just like many of you are. And I grew up in northeast of Los Angeles. And when I came to UCSD, I did not have the academic foundation necessary to do well at this school. And I came into the school wanting to pursue bioengineering because it's the coolest thing ever. At the time, I was super excited about the technology and what was out there. And one of the professors that really inspired me was Dr. Sangeeta Bhatia. She used to be a professor at UCSD in bioengineering. She has since moved on to MIT. But at the time, when I saw her work, I was just simply amazed. At the time, she was working with liver cells, and she wanted them to function outside of the body. And the whole thought of you coming in, needing an organ, then the scientist grows the organ and just implants it, I think that whole concept is just awesome. And so I wanted to work on artificial organs if I were to pursue bioengineering. And my primary concern, so these are my intentions for going into bioengineering. I wanted to go in because I wanted to save lives and I wanted to impact society in a positive way. So my intentions weren't to, make money or whatever it may be. It was to save lives. So this was my plan when I walked in freshman year. I was going to get my bachelor's in bioengineering. I was going to get my master's in bioengineering. I was also going to get my PhD in bioengineering. And my whole career was going to be dedicated to bioengineering. And the next 40 to 50 years was purely live, breathe, and die in this field. So I was super, super focused, and I was super motivated to pursue my goals. But I applied undeclared. One of my counselors told me that it would better my chances of getting accepted into college if I had applied into a major that was not impacted or undeclared. And so I applied in undeclared, but I knew exactly what I wanted to do. And so the first day of school, I had already talked to the department, and I told them, this major is impacted. How do I apply? And they told me, you're going to take these 9 engineering classes, or 9 lower division classes, and I was going to take them, and they're going to rank us by GPA. The top 10 get in to the major. And I was doing so well my first quarter. I was doing actually phenomenal, and then I hit physics. I had no background in physics. I'd never seen physics before, really, because when I took it in high school, we went to school 5 days a week. 4 out of the 5 days we'd be watching Mythbusters. That's all we did. And it's not an understatement. And so, no background in physics. And I was quiet. I was quiet as well. And so when I took physics, I didn't tap into the resources, meaning I didn't talk to the TA. I didn't outreach to my professors or anything like that. All I had was the book. I did not even do a Google search on anything. It was just a book, no solutions, whatever, just a book. And I was always an entire week behind. And those of you who have taken physics know we have weekly quizzes. And that did not work out well for me. So it resulted in my poor performance in physics, but if you ask me right now, I'll tell you that I have absolutely no regrets, because I did try my best. I did it the honest way. It was all I could do at the time. And so I applied, and I waited. And I was getting ready for class fall sophomore year, and I get this email. And that day, I just dropped everything. I put my backpack down and I didn't even know what to think, because as you already saw, my vision of the next 40 to 50 years was laid out. And seeing this email, I was devastated. I'd been shattered into a million different pieces, and I didn't even know how to think. And for a year and a half, I could not talk about this without crying. It was just devastating. So I had the next 40 years planned, but I did not know what I was going to do next quarter. And that's the 180 turn for me. So every time I think about this story, I think about this quote by Randy Pausch, who said it in a series of last lectures before he died of pancreatic cancer. We cannot change the cards we are dealt, just how we play the hand. And I keep reminding myself that. And so this was the domain of bioengineering, and somehow I ended up in structural. To this day, I still don't know why I picked structural. I wanted to stay in engineering because I like to build things, I like to tinker with things, so I didn't want to branch off from engineering, but at the same time, when you figured out the right major, everything else becomes irrelevant. And so that's why I ended up in structural, and this is what you do. Bridges, dams, buildings, whatever, modeling. And that is what I've been seeing for the past 2 years. And so I was unwilling to let this rejection stop me. I wanted to get exposure to laboratory work, so this is the environment I wanted to be in. But at the same time, I did not want to take biology courses or bioengineering. Well, I can't take bioengineering courses, but I didn't want to dilute my structural engineering classes, essentially. And I had to work with what I had. And there was this endless search for a year and a half into my career for laboratory work. And as you can imagine, if you approach a biochemistry professor or a biology professor, they don't know what to do with you if you're a structural engineer. To them, you're kind of, what am I supposed to do with you? You don't have the organic chemistry, you don't have the molecular biology, you don't have any of the chemistry background necessary to function in this lab. And so I just kept getting turned down over and over and over. And I hit a turning point. I was talking to Professor Paddock about research. This is kind of not even a turning point, it was rock bottom. I was talking to Professor Paddock, one of my professors, about research. And we were talking, I set up a meeting with him. We were standing outside of APNM, and it was in the morning, so it was cold. And he said, why don't we go out into where it's sunnier? And then I got there, and then we were standing right there, and before I even had a chance to speak, bird pooped all. Bird poop landed on my head, and it was just a mess. It was one of the worst experiences I've had with contacting a professor. You can just imagine it all over my head, and you can also imagine that conversation did not last long because it was awkward. I was clearly talking to a professor with bird poop on my head, so he just told me to go away. So that was the point where I said, okay, nature's not letting me do this, the department's not letting me do this, there has to be other ways. And that's when I realized experience is not gained in one place. And that's when I outreached to one of my friends. I reached out to her and I told her, I'm not doing anything. I'm sitting in my room all day. And she was amazing in that she told me, if you want to get involved in bioengineering, this is the way to write cover letters. This is how you get involved. You can get involved with teams as well. And teams, I didn't even consider teams before. All I was thinking was this one-way path research, and I did not realize how important teams were. And she introduced me to Engineering World Health, but at the time the applications were closed and I felt like the projects were already in progress, so I didn't pick up that team. But I kept teams in mind. And so literally at the beginning of 2013, I talked to Tim, and he said, do you want to join the Near Space Balloon team? And because of what Malika told me about teams and about getting involved, I said, okay, why not? Because I know it seems unrelated to bioengineering. It's not even the path that I want to go down on. It seems more aerospace, right? So now I'm not even structural. And so he said, you want to join? And I said, okay. And I worked on the command module, which I will be talking about in a second. And then at Karcher, another TA of mine from when I was taking a course, I told him about my situation, and he said, okay, there's a bioengineering student that came to our mechanical engineering lab, and he's working on a glaucoma project. He's just starting, and do you want to join in? And I, of course, said yes, but it was more on the medical device side of things, which is not something I really wanted to pursue in bioengineering, but I took the chance anyway. And by April, based on these two experiences, I emailed one of the biophysics professor on the off chance that she'll even reply, because in the past they don't reply. And I got an interview with her. She spoke to me about the tracker project, and that's when I got into my second lab. And then by September, I had gotten into a bioengineering lab, which went full circle for me. I finally molded. It took this path to get to here, but I finally got into a bioengineering lab. It was the most exciting time ever. For this particular lab, I applied online. We went through 2 rounds of interviews, and I was dead certain that I was not going to get the job, just because any molecular biology, bioengineering student could have knocked me out of the water. But I'll tell you later why I got the job. And it was for a lab assistant, which I'll talk about later too. So let's start with the near space balloon team, which I got involved in the beginning of last year. So as Tessina already mentioned, the near space balloon team, we launched these huge balloons that you see right there. This at the starting is probably 4 feet wide or so. And we launched these balloons for a purpose, to conduct experiments, whether it is to capture pressure, altitude, temperature, humidity, whatever. We send up these experiments and we do them at near space, and then we retrieve the payload in order to see what's going on in near space. And sometimes we'll also have a specific altitude target. So let's say we want to launch because we want to hit 50,000 feet. Or sometimes we'll also have joint projects with K through 12 and other organizations that want to do their launches. And so here's a schematic of what happens. It goes up, and then due to the pressure difference, you get the balloon pops and then it drops. You collect the data, and you get these beautiful pictures of Earth as the balloon is ascending or descending. And for my particular part in the balloon team, I was put on the command module section. At the time, we were launching these balloons with their sensors and everything, and at the end of the launch, when the balloon drops, that's when we collect data. But Tim, who led this project, had a vision that maybe we can get this information real time. And that's where we set out to build the command module, which its components are pretty basic. You have a microhard, which is a modem that would relay the information to the ground station. You have an Arduino Due, which is a microcontroller that takes information from all of these sensors, packages them, and then relays them to the microhard, which relays information to the ground station. And this is just power. So that was the concept of the command module, and I felt completely out of my comfort zone, because I hadn't programmed in C since I took the C class, and I had no experience with Arduino, no experience with sensors. And when we worked on this project, I realized that if you stand back and you look at the scale of this project, it had electrical engineering, you had computer science, because you had to program in C to get these microcontrollers to work. And then there's hardware and structural soundness, which involves mechanical engineering and structural engineering. So this was my first exposure to a real project that involved multiple disciplines and not just what I assumed it to be. And we built it. It was up and running, and we're hoping to get it to launch in our near future launches. So here you can see the Arduino Due. And then you can see all the sensors popping out on the side, but you can't see it in this picture. But yeah, we put it together, and I learned so much from this that I was able to, as Tessina mentioned, run those workshops, which was insane to me because it had only been 3 months of training with Tim. And so for future work, we want to develop a ground station, so the small computer running on a Raspberry Pi that would get us the live feedback we wanted. And we need to test the elasticity because of the balloon, because it affects how much helium we put into the balloon. And we have future launches planned, and maybe possibly more Arduino projects. So if you're interested, talk to me after. and hopefully you can get involved. So as you'll notice, I'm glossing through all of my research and all of my projects because I want to show you the diversity, so standing back and looking at it full scale. If you want the details to everything, definitely talk to me about it, and I'll let you know how it works out. So the glaucoma project is in Professor Taki's lab, and for this particular project, our goal was to build a biomedical device to track the pressure changes in the eye. And so when you have glaucoma, essentially your eye pressure increases and it presses against this optic nerve, and you eventually go blind. You progressively go blind if you don't notice, so this is what a person with glaucoma would experience. So this is normal vision, and then you end up with blurred vision, and then almost no vision at all. And people don't notice that they have glaucoma because if you turn your head, your blindness or your narrowness goes unnoticed because you're turning and you're seeing the view that you think you should be seeing when it's not the full view. So we set out to work on this project. When I first did research on this project, I realized how inefficient one of the leading standards for detecting eye pressure was, in that you go to the doctor and they apply an eye puff, and that flattens your cornea, which is the thickness of your eye. It flattens your cornea, and that's it. The amount of force that it takes to flatten the cornea is indirectly related to pressure, or at least that's what they're assuming. And there's two issues with this. One, it's inaccurate because eye pressure changes and fluctuates throughout the day, so if you go to the doctor once, then you just got only one data point, and that's not good enough. And there's variability. Everybody's eye thickness is different, and so for them to measure this force on there is not considering or accounting for the thickness in the eye. And so there was a need for direct and continuous monitoring. One of our biggest design constraints for this project was the smallness of the actual device. It could only be less than 1 millimeter cubed of space. And so when I looked at this project and I stand back, it's not a bioengineering project. It was a combination of material science, mechanical engineering, solid mechanics, and nanoengineering. And so, again, I walked into this project thinking it would be bioengineering, just bioengineering, and it's clearly not. So our concept is very, very, very simple. We have 2 acrylic plates, and we have a polymer in the middle. The pressure is applied, and that polymer compresses. And because of this compression, you get a direct reading of the area, which should be linearly related to the pressure that's being applied. And so we set up everything. We have the camera detecting the changes in the area. We have LabVIEW taking that information and computing, what the area is and what the pressure is associated with that. And this is what we see. And so before we went to real testing, we also did finite element analysis to make sure that the concept was sound. And so as you can see, you do get this linear relationship between normalized area and pressure, and the finite element model does show that there is even displacement between the 2 sides when it expands. And then we went to real testing, and we all saw the same linear relationship, so this confirmed that the concept does work. Sensitivity is definitely still an issue, but at least we were getting a linear relationship. And then we hit the first big bump of this project, which was biocompatibility. When we added the casing to this particular device to make it biocompatible, you sort of get this drifting effect that we don't know what's causing it. And so So over time, what you end up with after a bunch of runs is that the amount of area detected by the computer gets less and less and less. And this is not what you want when you look at your data. It should be one single line that's linear, and there shouldn't be this much variability in the data. And so currently I am in the progress of figuring out and isolating this drifting effect. The grad student thinks that there's slipping involved, but I don't think that that's the reason why we're getting less and less pressure or sensitivity. And then the next part of the project, after we isolate the drifting and figure out what caused it, was miniaturizing and also perhaps changing the design so that our devices would be more sensitive. So that would involve adding these micro pillars inside instead of just one column. And so that's the scope and that's the scale of the glaucoma project. And now I'm going to move on to the biophysics lab. So this one's actually a really cool lab that I joined. So this particular lab is all about planarians and regeneration. These planarians have the capability of regenerating. So if you cut them in their head, right here, so here I decapitated the worm, within a couple of hours you'll see stem cells and stem cells begin to migrate in the region where you cut it. And within a week, the head would fully be regrown, which is insane to me. Every time I see this, I'm just amazed. And so I think I will show you a video of it dividing. So the way these planarians, these asexual planarians reproduce is that they split themselves in half. Not in half, but they split themselves in a particular region. So is it going? So here's a worm dividing. And I want you to pay attention to this region at the end and this region right here, which is pretty cool. So give it a second. It's trying to elongate and pull itself apart. So it's pretty difficult. So you'll begin to see the migration of cells in this region and in this region, and then it's gonna try to pull itself apart because of that. So there it is. You can see the cells growing here and the cells growing here. And then you end up with this really, really thin region, and then it yanks itself apart. And so this part will become another worm, and this part will just regenerate its tail. And for those of you in structural engineering, or those of you who have taken SE2, this is your classic tensile test. So it's amazing how we do these testings in engineering to find the amount of force that it takes to pull on a material, and here these worms are just doing that in nature. So I think that's pretty awesome. So now the question comes, where does the memory go if I cut its nervous system? So if you decapitate it here, if the memory was stored just like humans, if it's stored in the head region, where does the memory go if I cut it? And if it regrows, is the memory still there? So that was one of the primary interests behind the tracker. This is the tracker robot. It makes sounds like R2-D2, and I should have gotten a video, but I didn't. So this tracker was developed by Mark Stone, a sophomore from Princeton, and when it got to UCSD, it stopped working for some reason. So I was taken into this lab to work on this particular project. The code for this runs on LabVIEW OpenCV libraries that are programmed in C++. And so this is one of the other applications of programming that I had to really implement after taking a class. And the whole idea behind this is that it tracks the center of mass of the worm. So as the worm is swimming around this arena, so it's swimming, the tracker is going to follow with the worm, both in the Y direction and in the X direction. And from this, we were hoping to design experiments that would really tell us the behavior of the worm. So if you cut its head, would it still behave the same after the head's been regenerated? And so one of the preliminary tests that I did very recently was the temperature gradient. So here you see a gradient. This side is 15 degrees, this side is 25 degrees, and the incubation of these worms, they go in 19 degrees, so that's around this region. And you can see across all the data that the worms are again and again migrating towards the colder region, or the more favorable region, which is not hot. And you can see the path of the worm. So here it starts off maybe at the center and it goes around, but primarily it ends up in this region, which is what we wanted. So for future testing, could we condition these worms to react the same way every time, and then cut them, have them regenerate, and would that yield the same patterns? So the behavior studies that we wanted to do in the future was perhaps electrical shock, magnetic field, food. So maybe condition them to, to find food you need to go to this specific part of the arena, or at this specific time. We could coerce them with light. And so hopefully we can, for now, for me at least, I'm going to try to optimize the stability of the temperature gradient so it's not shifting. But yeah, that's what we're planning to do in the future, and I'm super excited. And the last one is the Mercola lab. Oh, by the way, I'm doing multiple projects in each of these labs. I just did not list them because it would make this presentation super long. So for the Mercola lab, so I'm not going to sugarcoat this. A lab assistant is essentially the person that cleans up after the scientist. So that includes inventory, restocking the solutions, and all that other stuff. But I was hired for 10 hours. That stuff that I just mentioned only takes me about a couple hours to do. So you can imagine the rest of the hours that I am there, I'm working with a scientist on his projects. And for me to not have molecular biology, organic chemistry, or any of those topics, for me it was the most difficult thing in the world to do all of these things and not know what I'm doing. And the lucky part about this particular lab is that they are so committed to helping me learn this stuff. And so the reason why I got the job, when I interviewed with the lab manager the second time around, and I just honestly told him I don't know anything. I really don't. I haven't been in this field. I haven't taken the classes or any of the laboratory classes. And at the end of the interview, when I got the job, he told me that, you know, I wasn't looking for somebody that had the experience. Some people did list on their resume that they had laboratory or they took courses, but I was actually looking for was a leader, because whoever was going to this lab was going to build the lab from the ground up again without my supervision. I was going to be over there. And so he wasn't looking for somebody that was able to follow a recipe on what, you know, the protocols that you have to do. He was actually looking for somebody who can manage a lab when he's not there. And so that was what made or break the deal. And I was lucky enough to have been involved in so many things. And I guess I just gave the aura that I was a leader, but I didn't think I did, because I was just constantly saying I don't know. But anyway, so that's how I was able to get into this lab. And I think it is so important for me to have learned these fundamental things, even if a normal bioengineer or a normal biology major would find these protocols and these I guess technical procedures so simple and so simple and I guess normal to that environment. But for me as a structural engineer, this is a completely different environment, and I super cherish the time that I am here all the time. And I have been approached with future projects, such as working with cardiomyocytes, which are essentially heart cells that are going to differentiate into essentially heart cells. And so I haven't picked these projects up because I had so many things to do, but hopefully in the future I'll be more and more involved with this lab. Okay, so I've talked about all of these projects and all the things that I've done in them. One thing that I did not mention was tutoring, which I have been doing since my freshman year. Immediately after I took MA9, I just tutored. And it has been an amazing experience being in this class because it has trained me to adapt to every single engineer that I talk to. That is one of the key things that people lack because, well, you see things in your own way and perhaps you see things in your friends' perspectives or those around you, but to be able to talk to every single engineer and look at their computer screen and be like, okay, what are you thinking? That was one of the amazing parts about tutoring, which was the interaction between all of these engineers. And being able to talk to, engineers from aerospace, chemical engineering, nanoengineering, bioengineering at one point. And it was just an amazing because people bring different things to the table and they think differently. So being able to see in their eyes what they're trying to do with their homework or code is an experience that I think everyone should have. So from this, I gained leadership, organization, my learning process, and all of this good stuff that comes with tutoring that people don't realize. And so you're probably wondering, well, how did you connect everything? Everything's just scattered. That's not true. From tutoring, I reinforced all of my programming skills, so I have very, very strong programming skills. And from there, I took it over to the balloon team when we programmed the command module. And then from that, I showed my students, I showed my students the applications of programming so they don't feel like it's useless or they can't apply it. And then I took that to the Collins lab, which had a controller that was running on C. So it was a combination of balloon team and tutoring. And the Talkie lab, I took the knowledge that I got from analyzing data, setting up an experiment, and I fed it into the Talkie lab and programming from the balloon team as well. So everything was interconnected for me, and the highlight of this is probably my research skills and my programming skills and my engineering skills as well. So this was 2013 and 2014 in a nutshell. I was involved with so many different fields. It was insane. It was just insane. I can't even believe it's been only a year as well. So after 4 years of interacting with hundreds of students and talking to faculty, talking to graduate students, talking to people in different stages of their career, I realized, does it matter? Does it really matter where we start? Because a lot of us, I didn't feel like I was the only one, a lot of us come in with this laser-focused idea of what we should be doing, right? We have this kind of fixed idea that, I need to pick that right major. I need to go into this field, go in full force, and I'm behind and all of that stuff. Does it matter? No, not really. It does not matter where you start, but you have to keep the goal in mind. And also, if this had happened, if the failures to get into bioengineering had happened in a million different universes, I think all the outcomes would have been the same, and it would be that I tried to shape the experience I wanted to have and not let the rejection define what I wanted to do or limit me as well. And so, shape the experience you want to have. So, one of the biggest misconceptions after talking to so many people of what they think the primary concern of the undergraduate degree is if to fill up your resume. No, it's not. It's not to fill up your resume at all. Is it to get the experience because you think everyone else is getting the experience? No, not really. Is it just to take courses? No. To know your field better? No. So these are all of the traits that you would get if you joined taking classes, going into laboratory, going into internships and team organizations. Now, the list goes on. I can't list all of them. I list only the main ones that I saw. But you get so much of the practicality of being an engineer and being a scientist and all of these things that your major and where you come from and where you start at becomes almost irrelevant. Why, and why do we want to do all of this? So what is the biggest concern for graduates today is that we have not refined any of these skills adequately. So you go into the workforce and people feel like, you're not being trained enough or you don't know enough and you're still starting out. We have not refined all of these, and what's the solution? It's to be involved and also be aware. When you join an organization, don't let the opportunities come to you and you're going to wait until you gain the experience you need. It's not going to come as fast. If you are aware of the areas that you want to improve, it makes it so much easier. So say you join an organization and you say, okay, I want to work on my team building skills, or I want to work on my design skills, or perhaps even my research skills. If you come in with that particular goal, now all the other opportunities will come as well, but you come in with that particular goal and you put yourself in the position that will really show your leadership or really show your research skills. That's how you hone in and refine each of these things. Not everybody's going to be good at every single thing, so the rule of thumb is to pick some skills and be so good at it that nobody can beat you on it. And also one's own voice. So who are you as an engineer? So if I threw you out into the real world right now, how are you going to pick and solve these engineering problems and decompose them? So these laboratory internships and team organizations really highlight those skills, and for you to be aware of those things is super, super important. So why are we doing all of this? Why are we doing laboratory work? Are we trying to get that job that we want? Is that it? The answer is no. All of these skills that you gain in your undergraduate, if you were to be involved, is funneled into your success later in life. So the ability to dissect problems and manage them into these milestones that you're able to achieve, communication, innovation, and the ability to be self-sufficient, self-sustaining, Your ability to ask questions that actually push for progress, right? So you're not asking these pointless questions that you don't know what direction you're going into, and tapping into resources. So these fundamental skills actually contribute largely to your success. There are more, trust me, there are so many more skills, but these are fundamental because it allows you to be adaptive. So I have not listed major or relevance in any of these. And so your ability to have these skills is the reason why you'll be successful. And all of that is funneled into passion, which is fueled by either you're curious, you're interested, you're frustrated, or you're bored. And one of the biggest things about passion is that people assume that you're going to go find your passion. Passion actually can't be found. It's only developed. And when I say I have passion for something, it's not, I can't be passionate about something I just learned about 2 hours ago. So it requires two things. I'm sorry it's so low down here. It requires time and knowledge, and adequate knowledge. And that's how you build your passion for something. And also connections. When I got to UCSD, I don't know why, but a lot of people were just on this networking reel where I just felt like everybody was making friends and really networking. So you'd meet somebody in 2 seconds, they'd have your Facebook profile pulled up. When I talk about connections fueling this passion as well, connections are not the type of connections where you're networking and you're meeting friends. The connections that I'm talking about are long-lasting connections with faculty members, with your teaching assistants, your graduate students, all the people that are able to believe in you. So connections are actually getting people to believe in you, believe in your vision, believe in your potential, and really understand where you're going in life. And so these connections are the ones that build the great recommendation letters. They're the ones that get you, into these internships as well. So not networking. I'm not talking about networking when I talk about connections. Okay, so the last part of my talk, I want to talk about exploration. So as you've seen today, I showed you different domains in engineering, and when I go into them I have this narrow idea of what it is, and all of a sudden it blows up to these projects that involve so many fields. And so I realized that the boundaries between the fields, all of them, physics, cognitive science, neuroscience, bioengineering, mechanical, whatever field, they're there because we put them there. Okay, so you can see physics and biology pretty much in the same light, you're just looking at them in different angles. And while we are pursuing our undergraduate degree, I think it is very important for us to step back and look at the bigger picture. I think it's super important that we think about what our individual role is in our community or our society, and how we can take our knowledge and really push for progress. And for me, the original motivation to go into bioengineering, to do all of these things, is still there. It is to save lives and positively impact society. So always, I want you to reflect and really think about how you feel about what the difference you can make in society based on your knowledge here at UCSD, or based on your experiences as well. So how have we been affected, and how we can affect others? And this is what progress is humanity. This is how we push each other, and this is how we push ourselves. And so the take-home message to this seminar is that diversity is very important, but that's not telling you to go major in 3 different things. Your classes that you take, it doesn't matter which major, give you the platform. The application is completely up to you. And I think for me, I thought that bioengineers do bioengineering things and that's it. And that's not the way to think. That's not the way to think if you are aiming for innovation. It's the fusion between fields, and it's the diverse applications. So if you're a physicist, you can take that into engineering. If you're a cognitive science major, you can take that knowledge and bring it into music. So it's very important. So the second take-home message is, let us not define ourselves by the discipline, major, or field, but by the problems we seek to solve and the approaches we choose to take. And this is one of the most kind of defining moments for me, when I realized from all of these faculty members that really it does not matter what you did 50 years ago, really. So if you've asked any faculty member what they are doing, they'll talk about their current research. They're not going to talk about something they did, way back in their undergrad and be like, that was the highlight. No, they're going to talk about the current progress, and their projects are constantly changing, and so they define themselves based on what they're currently doing, and that's also constantly changing. And I also wanted to say this because if you're a physicist or a cognitive science and you spend the next 20 years solving engineering problems, even though you got a physics background and you're solving engineering problems, I would more likely consider you as an engineer more so than a physicist. So it's really not what major you are in that defines you, it's the problems that you solve. And so let us empower and be empowered. Let us incorporate diversity and unite a global society. Let us enable and innovate, and let us engineer. Thank you. Man.